Welcome to The Explainer. Today, we're investigating a massive cosmic mystery, and honestly, a mind-bending plot twist that challenges literally everything we know about the universe. If you follow astrophysics, you know that the dark sector is arguably the greatest unresolved puzzle in modern science. But what if the answer isn't something we can just put in a particle collider? For decades now, we've been hunting for these invisible dark matter particles. But what if we've been looking for the entirely wrong thing? A fascinating new paper asks a really profound question. What if dark matter is actually a geometrical defect, like a physical scar left over from the very dawn of the universe? It's a radical shift in perspective, moving from a universe filled with unseen microscopic dots to a universe built on an unseen warped foundation. To understand why this is such a game changer, we kind of have to look at the cosmic crime scene itself, the residual gravitational component. We know galaxies spin way too fast to be held together just by their visible matter. You know, the stars, the gas, the dust. There is a massive gravitational grip keeping these galaxies from just flying apart. The prime suspect for decades has been particulate cold dark matter. But despite our most sensitive detectors, these particles remain stubbornly invisible. We see their gravitational effect for sure, but we just can't find the physical substance.
So the standard model, lambda CDM, assumes that invisible particle halos gather together, trap normal matter, and that matter eventually collapses to form the galaxy shapes we see today. But dynamic vacuum field theory, or DVFT, completely flips the script. It suggests gravity comes from geometric defects in the vacuum itself. In DVFT, the vacuum isn't just empty space, it's a physical, dynamical field. And when this field was forming right after the Big Bang, it didn't settle perfectly. The paper proposes this wild new sequence of events. It starts with something called a tachyonic vacuum rolldown. Imagine the early universe rapidly cooling and just snapping into a new state. Because this happens so incredibly fast, the vacuum can't synchronize perfectly everywhere. It leaves behind these primordial defects, physical scars in the vacuum. These defects then act as giant gravitational traps for normal baryonic matter, which ultimately dictates the final shape of the galaxy.
Right at the heart of this theory is the Kibble-Zurek defect. Honestly, think of it like a giant cosmic pothole. It's a frozen scar where the phases of the vacuum didn't quite match up during that rapid cooling process. This trapped mismatch creates a depression in the amplitude of the vacuum field, and that acts exactly like an immense gravity well. So instead of a cloud of invisible particles pulling on stars, you have a literal dip in the geometry of space-time itself doing the pulling. This leads to just a gorgeous concept. The paper states, the baryonic galaxy is therefore not the origin of morphology. It is the visible tracer of a deeper defect geometry. Think about what that means. It's a massive paradigm shift. It means that the brilliant, swirling shapes of galaxies aren't just random accidents of gas and dust bumping into each other over billions of years. No, galaxies are cosmic fossils. They are the glowing, visible tracers of the invisible, primordial vacuum scars they sit inside. And what's absolutely crazy is how perfectly the math maps these defect shapes to the actual galaxy shapes we observe through our telescopes. A simple, nearly spherical defect leads to a round elliptical galaxy. An oblate or flattened defect gives you a disk galaxy. But here is the kicker. A twisted oblate defect gives birth to the classic spiral galaxy. The spiral arms aren't just waves of gas. They are matter caught in a spinning vortex of the vacuum itself. How cool is that?
But you know, a beautiful theory just isn't enough in science. We need hard data. To test this thrilling hypothesis, the author turns to the MaNGA dataset, which is an incredibly rich collection of data from over 6,000 galaxies. The goal here is to see if the visible structures of these galaxies genuinely correlate with the underlying, hidden gravitational geometry that DVFT predicts. If this theory holds water, the shape of the visible galaxy should be strongly linked to the shape of its hidden gravitational well. When the photometric classes in the data are analyzed, the exact fingerprints we are looking for show up. Disk-like systems are visibly more flattened, occupying a higher range of ellipticity, while bulge-like systems are way rounder. This perfectly matches the core DVFT prediction, that flattened oblate defects create disk galaxies, while spherical defects create bulge-like elliptical galaxies. The visible structure is directly, literally echoing the proposed underlying vacuum geometry.
Now, to be fair, This pilot data doesn't definitively prove DVFT is the undisputed law of the universe just yet, but it does something equally crucial. It confirms that this radical alternative ontology is highly testable with our current telescope data. It moves DVFT from a purely mathematical philosophy right into the realm of rigorous observational science. We actually have the tools to prove it right or prove it wrong.
Let's zoom in on a specific crime scene. The paper highlights the galaxy NGC 3198. This is a really critical case study because it allows astronomers to separate the local, messy gas streaming of the galaxy's arms from the true, global, hidden gravitational support. If we're ever going to understand what the dark sector really is, we absolutely have to isolate the grand gravitational scaffold from the local baryonic noise.
Take the flat rotation curve for NGC 3198, for example. The velocity rises and then just stays incredibly stable and flat in the outer edges. It maintains a highly coherent outer circular velocity. What this proves is the existence of a stable, hidden gravitational scaffold. In the standard model, we'd say, okay, this is a massive cloud of particles. But in DVFT, this perfectly smooth, coherent outer rotation is exactly what you'd expect from the incredibly stable amplitude depression of a Kibble-Zurek vacuum defect.
And the math completely backs this up. When running the statistical diagnostics on NGC 3198, the new math of the DVFT finite coherence core actually fits this specific galaxy's telescope data better than the standard particle model. The comparison yields a Bayesian information criterion difference of plus 20.66. To put that into perspective, in statistical terms, anything over 10 is considered very strong evidence. So almost 30 is a massive margin. It means the observational data heavily prefers the shape of a vacuum defect well over a standard particle dark matter halo.
It gets even more compelling when we look at the really big picture. When the models are extrapolated to massive weak lensing scales of 1 megaparsec, so way out beyond the visible edge of the galaxies, the Kibble-Zurek defect model remains perfectly flat with a ratio of 1.003. Meanwhile, the standard particle model declines substantially to 0.531. Recent weak lensing observations in the real world show that gravitational pull stays incredibly flat at these massive distances, a behavior the DVFT predicts naturally. So, where do we go from here? Well, the best part is that this theory is entirely falsifiable, which is the hallmark of great science. It relies on upcoming observations from next-generation telescopes, like the James Webb Space Telescope, Euclid, and the Square Kilometre Array, to either prove or destroy it. DVFT predicts that at high redshifts, when we look way back in time to the early universe, galaxies should be more irregular because the vacuum scars haven't fully relaxed yet. If future data shows these exact correlations, DVFT gains massive support. If they vanish, the theory fails. As the author neutrally notes, this paper isn't a final, airtight proof. What it does is open a concrete, mathematically grounded alternative to the cold dark matter paradigm. It gives us a completely new framework to understand exactly why galaxies are shaped the way they are, relying on the physical properties of the vacuum itself, rather than some undiscovered particle. So I'll leave you with this final thought as we continue to gaze into the cosmos. When we finally close the case on the dark matter mystery, will we be holding a new, elusive particle in our hands? Or will we realize we've been staring directly at the intricate, primordial scars of the vacuum itself all along? Thank you for joining me on this explainer, and keep your eyes on the stars.